Um, when Adele asked me to talk about this, I had one idea in mind about kind of who the audience is and what sort of questions people might have. And I think that that may change. So I'm going to kind of try to at least get the basic components together. What are the main concerns that people might think about? And then see if we can ask the appropriate questions that are closer to what people are actually interested in. So I'm going to kind of talk about the geo-exchange types. So the thing that makes a geothermal heat pump system different from a water source heat pump system is simply that it's exchanged with the ground as opposed to being exchanged with a river or a lake or some other source of a heat source or sink. So then we're going to talk a little bit about water source heat pumps that, even though they're actually quite old, people are less familiar with them these days than air source heat pumps. And then I'll talk a little bit about the comparison to air source heat pumps. And then we'll talk about distribution systems. And I know that sounds like a lot. And I think what I'm going to hope to do is focus on the geo-exchange component, and then as kind of introduce those other things, and then see what sorts of questions come up, and we can go from there. So context here, if you think about the goal is, here we are right now, or 2020 is the reference year, and you can see we basically import into the state a whole lot of natural gas and a whole lot of petroleum. And, a good almost half of all that gas goes to buildings. And the portion of the gas and a fair portion of the petroleum that goes to buildings goes there for only one reason, which is to make heat or hot water, with making heat. That's it. So if we want to end up in 2050 not importing a lot of petroleum and natural gas, this is, again, the Massachusetts decarbonization roadmap, and we could fight about the details on this, but the basic story is more electricity generation, a lot of it from offshore wind, but the total amount of energy going into buildings is considerably lower. And all of that is, or the vast majority of that is electricity. And that means that all of that heat is being produced with electricity. And the reason that it can be considerably lower is the assumption that we're using heat pumps of some sort, and therefore the amount of energy that's going in can be divided essentially by 3. We're assuming that the heat pumps are 300% efficient or better. So basics of heat pumps, then I'll assume you guys either know this stuff or don't need to know it in order to get the basic ideas, which is basically we've got a compression, a vapor compression system. We use an evaporator to lose heat to to gain heat as it's evaporating the refrigerant, and then that refrigerant is a medium pressure, medium temperature vapor, and it gets compressed, and that compression turns it into a high temperature, high pressure vapor. And then it goes into the condenser where it can lose heat. And as it loses heat, it turns into a medium temperature, high pressure liquid. And the key trick here is that we have this thermal expansion valve. And if you've ever had like compressed air and you tried to clean something with compressed air and then you felt the can get really, really cold, that's because you've taken this high pressure liquid and you've released it. And as it turns to a lower pressure, it drops its temperature a whole lot. That's the basic system, and that's how we move heat from one place to another. Heat pumps are air conditioners that work in both directions. Typically, these have been air source heat pumps, right? So in the summer, they take heat out of the house and reject it to the outside. And in the winter, they take heat out of the outside and deposit it on the inside of the house. And the efficiency is the amount of work that we have to do to compress that refrigerant and make it move through the refrigeration cycle. So it's basically how much heat, if we're in heating mode, how much heat do we get out of it for how much work, right? And so the term that we tend to use for this efficiency is coefficient of performance. And a key thing to know here is that in heating, we're taking the heat that we took out of the low source, the low temperature source, plus the heat that we put in for compression. We actually get that. And you combine those together, and that's the amount of heat that we're delivering to the system. Now, in cooling, that extra heat that we put in for electrical heat energy to do the compression, we have to reject that too. It's not a benefit to us. And that's going to be important when we think about the difference between the balance between heating and cooling in ground source heat pumps in particular. So if you've ever gone and bought a window air conditioner, you might have found that it had an energy efficiency ratio of around 8.3. And that's because if you put in 12 kilowatts of energy and you get out 100 kBTUs per hour, that's usually often a rating, that's something like that for air conditioning, you would get an energy efficiency ratio which mixes these two units, kilowatts and kBTUH, or watts and BTUs per hour, in a silly American way that we do things. But if you put them into the same units, then you can get a coefficient of performance. So if we can convert our BTU per hour to watts, then we can get a coefficient of performance. That's just setting our terms, really. The key thing to understand, though, forget about all that other stuff, is that the coefficient of performance is a function of the height of the temperature lift. How far do you have to move that temperature uphill? It's right. If what you're doing is doing work to raise temperature from a low temperature source to a higher temperature source, whether you're cooling or heating, you're always trying to move it from one place to the other. If we're in heating, if we're in heating mode right now, our maximum theoretical coefficient of performance is going to be determined by the difference between the term on the top, which is the high temperature reservoir, or the heat that we want to deliver in this case, right? And the difference between the low temperature reservoir and the heat we want to deliver. So if that difference is really, really, really small, then the coefficient of performance can be really, really big. And the bigger that difference is at the bottom, the lower our maximum coefficient of performance can be, regardless of everything else we do. So that's the basic logic of geoexchange, is to say, let's reduce that temperature lift and let's make it be at the coldest times that we still have moderate temperatures to work with. So in theory, and we're going to talk about how it doesn't always work out this way, in our climate zone, roughly speaking, the ground, once you get below like 12 feet down, is roughly the average temperature of our location, which is, in the 50, 55 degree Fahrenheit range. And so that's represented by this line running across here. And you can see that the air temperatures, again, the average air temperatures, get quite low, and then they can get fairly high. And this is a ground temperature that's about something like 6 feet down. And you'll notice the ground temperature that when it's not all the way down below 12 feet or so is not exactly stable at 50 degrees Fahrenheit. It's actually going lower and going higher, and it's kind of out of sync with the seasons, right? If this is where the air temperature is, then it's not only lower, the high is a little bit lower, but it happens later. Basically, the ground is a giant thermal mass, right? It's just a big thermal battery. and it's gaining solar heat at that depth, so that it's actually gaining heat over time and then losing heat. And it's just modulating that like a thermal mass. So the heating temperatures that we might try to reach are up above 80 degrees Fahrenheit. And you can see there that the lift required, right, these green arrows, the thermal lift is much smaller if we had ground temperatures than if we had air temperatures in February. And if we were able to use those even higher ground temperatures, then the thermal lift would be even smaller in November and December. And for cooling, it gets even better, right? Cooling, we want to supply, basically, if we can supply 44-degree Fahrenheit water, we can do cooling and dehumidification. And I'm not going to get into why, but basically that's the kind of the key temperature for providing typical thermal comfort cooling. Well, here, the temperature that we have to drop, right, the temperature lift between inside and outside, is much, much smaller at the ground temperatures than it is out on the outside air temperatures. So that's the logic of why a geo-exchange system would be a good idea. So there are a bunch of different ways of trying to exchange your heat with the ground. Boreholes are expensive because you've got to do a lot of drilling and you tend to have to create a lot of them. And the heat exchange that each one of these can do is limited by the type of soil you have, how wet the soil is, how deep you are to bedrock, what kind of rock. It's a very geologically determined situation. And all of that, and you can't space them too closely together or they start to interact with each other and you lose your heat exchanger capability. So there are a bunch of reasons why boreholes are both very common because they're the most flexible. You can always just make more boreholes or make deeper boreholes and achieve the heat exchange capacity that you require, and the most expensive. But they do better when you have a limited land area. So if you have a large institution and you're trying to, you only have one sports field that you want to put a bunch of boreholes under, you'd be better off doing this one than the next closed loop system, which is typically done as their horizontal loop. They could be as little as 4 feet down under the ground. They tend to be done in these slinkies just because they take up a little bit less space, and it's basically this flexible pipe that's just set underground at a decent enough spacing. It's considerably less expensive, particularly if you're already doing a fair amount of excavation. So recently we were looking at a situation where we needed to do a major drainage, a place to do drainage storage. And since we were going to propose to do a large excavation under a parking lot, or under what would be a parking lot for that, we actually proposed to put a slinky loop system in that area because the excavation essentially was already done. And that's the big cost associated with this, the slinky loop technology. On the other hand, it requires a lot of area. So if you have a fairly large heating or cooling load, then it's going to take a really large surface area. So, we're talking a really, really large football field in order to satisfy the heating and cooling demand of maybe not such a huge school, for example. Among the most common, and historically, I would say the most common, especially in our area, is some form of an open loop system. It takes essentially the conventional well drilling that if you live in the hill towns or even many parts of Amherst, and even out here in getting up into the hill towns, you have to drill your own well, right? You got a lot of people who are on well water. The same technology that drills the well water works for this. And in fact, very often you can combine it with well water that is actually producing drinking water. So it depends on do you have a water resource? Can you extract enough water? And so you extract water, you put it through the heat exchanger, and then you send the water back into the ground. So this can be the lowest cost. However, because it's an open loop system, you're drawing up groundwater, and that groundwater is going to have minerals and potentially iron-eating bacteria and grit and debris. So you're going to need to filter it, or it clogs your heat exchanger, and then the whole thing goes bad. So it does tend to require filter maintenance. And I will say, so I don't have a whole lot of experience designing brand new geothermal systems, but I have a fair amount of experience helping people troubleshoot why their geothermal systems are behaving very badly, why they're costing them a lot of money, why they're actually, you know, using a whole lot of electricity when they were supposed to be tremendously efficient. And very often the answer has something to do with the way these open loop systems were designed. That's just been my own experience. So there's kind of a system that's like an open loop system. It still uses the same well drilling thing, although very often you're drilling much lower, because you actually have to drill into bedrock and you have to have the appropriate type of rock formation. But this is like a closed loop system in that you basically have the water that you extract getting put back into the same hole, right? The same well. And the nice thing about this is it uses conductive heat transfer, right? You're transferring heat from the ground to the well, and that's full of water, and the water is storing that heat. And it's essentially this thermal mass storage of heat from the ground. And if the water starts to get too cold, let's say it's in heating season and the water starts to get too cold, then you can actually have this emergency bleed, which will start to drop the water somewhere else. Either it's an injection well or spilling it on the ground or something else. And that the bleed causes a negative pressure inside the well, and that draws water, groundwater, into the well, which is new groundwater. And so now it's warmed it back up. So it's a way of dealing with an imbalanced system. So there is no best possible system. Each one has its own pluses and minuses. An open well, it often has the lowest first cost. It can be very efficient if well designed, because you've constantly got fresh ground temperature water. So that 50 degrees that we said was going to be the case actually probably might be the case all year round in this case. But the geology has to be just right. And you have a maintenance issue that I mentioned with filters. And that can sometimes become a really bad maintenance issue, although I can talk about how we can reduce those. And because you're interacting with groundwater, potentially drinking water, there are a bunch of regulatory issues that have to be dealt with, but it's very thermally stable. The standing column well, which is that kind of quasi-open system that I talked about, it's pretty efficient, but as you are returning water back to that same well, it's going to cool down a bit. And so now you're going to have to bleed it a little bit, and that gives you a penalty with your efficiency. It's going to cost more because you tend to have to drill a much deeper well. It works in more different types of geologies, and it potentially can have lower regulatory burdens if you're again going all the way through the bedrock, and if the geology is just right, basically. And then there are closed loop system, and I talked about a few different types, boreholes and slinky loops. And those ones tend to have the lowest efficiency because they really depend on the heat exchange with the ground. They cost more generally because you have to have more area. So that's more excavation, more drilling. Maintenance, they can be really, really good. The main benefit is that you really are a closed system, and you're not interacting with the environment other than thermally with the ground. And so that can be a real reason why it's easier to apply and you don't have to jump through as many hoops. So that's just the heat exchangers, and we're assuming that everything goes magically well with the heat pump. But in fact, what we really need to think about is the whole system efficiency. So we have a geo-exchange loop pump, right? You're running all this water. Either you're pulling water out of a well and then re-injecting it somewhere, or you're circulating water through potentially miles of piping. And both of those things can add a lot of energy to the demand of the system. And if we don't include that, we're really not including the whole system and how it works. And on the other side, once we've generated the heat, if we're heating, or chilled water for cooling, then we've got pumps that have to circulate water, or fans, if we're going directly to using a refrigerant to go directly to air, we've got fans that have to blow air, perhaps through ducts. And depending on how we've designed that, that can be a large increase in energy use. So we really, when we're comparing these systems, we always want to look at the system coefficient of performance, which is basically the useful heat that we get out divided by the energy we have to put in to run the compressor and the loop pump and the distribution pump or fans. So there are some designs. This is kind of the things you should look for if you're involved with designing a geo-exchange loop. If we have really, really large U-tube fields, that's a lot of friction in the pipes. That's just a lot of friction head that we've added to that pump. And that means we need a bigger pump and it's going to work harder. If we undersize the pipe, or we don't size the pipe for low friction, then we have a pump that has to work really hard to circulate that water through the pump, through the pipe. Long loop lengths. So we're better off with a manifold and a bunch of shorter loops than one really giant long loop where we've got a lot of static pressure we've got to fight. Systems that are designed for constant circulation in the geothermal system, that's, I will say, the biggest energy user that I've encountered when I've worked in various things where people, wanted me to help explain why their heat pumps were not working, or why they weren't saving them energy. Probably the biggest problem has been constant pumps that are on 100% of the time at full speed, regardless what the demand was, regardless of whether the compressor was on. You were just circulating that water as hard and as fast as you need to on that 1 hour of the year when it's the biggest demand possible. So constant circulation and fixed speeds. So a thing you should know about fluids and pumps is that if you can, if you cut the speed of the flow of the fluid through a system, in this case water, you can reduce the pump energy by the cube of that difference. So you get a really, really, really large reduction in energy from small reductions in pump speeds. And most of the time, a system that was designed for whatever its peak demand is, most of the time, it's not going to require the water to be moving at the design speed. So you can save a huge amount of energy and turbulence by reducing the pump speeds and having them respond to the temperatures required by the heat exchangers. Clogged filters, so this is for open loop systems, and open loop systems with a low water temperature, water table. So if you have to lift water a high height, that's going to add a huge amount of pump power that you require. And then on the distribution energy side, generally, water is an efficient way to move heat, and air is not energy dense at all. And that means you've got to move a lot of air, and that's a lot of fan power to move the same amount of heat as a small pump moving the same amount of heat. So generally, ducted forced air systems have a fairly large penalty to their system coefficient of performance. And with those ducted systems, high static pressure is going to increase your fan energy required. Fixed speed motors. Again, most of the time we don't require the full capacity of our systems. So if we have variable speed systems, then we can match the flow of whatever fluid, air or water, to the actual demand and save a lot of energy that way. If there was one message I would want to leave you with on this, is that an important characteristic is variable speed everything. Variable speed compressors, variable thermal expansion valves, variable pumps, variable speed fans. So the other thing that we tend to think about, most ground source heat pump systems, except the ones that are using advective heat flow, which is to say we're bringing in new groundwater, we want them to be generally in balance. And so during the heating season, right, we're extracting heat from the ground, and during the cooling season, we're sending heat to the ground. And if it's imbalanced, eventually it's going to become either too hot or too cold. And we solve that either by making a bigger, more expensive geoexchange field, or we have some system that allows it, like an open loop or standing column well, where we can move water in from elsewhere, or direct exchange with a moving water body like a river, or we have to find a way to make it balanced. So this is an example from a school system that I was working on recently. Now, they don't currently have cooling at all, but we assumed that they would want some. So these are the loads that they would have if we added cooling. What you can see is there's a whole lot more heating demand than there is heat rejection or to the ground. And so eventually this is going to be out of balance. And we can see this in lots of studies historically, where you have that thermal imbalance. And what, so this is a case in Montreal, for example, where over a 10-year period, as they extracted more heat than they deposited back in, eventually the water temperature returning from the ground was lower than freezing, which impacts that. Remember, we were aiming, the whole reason to do this geoexchange thing was to get nice warm water temperature that was constant, but over time we're dropping the temperature so that it isn't any better than an air source heat pump. Anyway, that can be a problem, and that's a problem that I've seen again in kind of my own investigations. Actually, the very first heat pump system I investigated was one where the ground was literally frozen and they were actually getting frost heaves in unexpected places. So the typical solution is just expand the geoexchange field even more, just make it bigger. And that way you can essentially stretch that 10-year period out to maybe 20, maybe 30 years without really noticing it. But that's a big oversize. Another solution, and one that I think is pretty cool, is actually using solar thermal energy in a place where you don't have a balance to just dump that heat energy in. Now, that's great if you've got a reason to have a solar thermal collector that is doing what it needs to be doing, and that has lots of times when it's actually oversized for what you need, which is to say almost all solar thermal collectors. So this is a nice way to marry solar thermal for, say, hot water. Let's say you had a swimming pool. You could heat the swimming pool and do season extension and have more heat production during the summer than you knew what to do with, and you could dump that in the ground. Here's just kind of a model of how that would work. And so in this particular case, that's what we suggested they do. And by adding the solar thermal, they got the heating and cooling into rough balance. You can have the same problem with too much cooling. So this is a hotel in Korea that's really got a climate regime quite similar to ours, but they just have a higher cooling load in this particular hotel. And so over time, the ground temperature became so hot that it's no longer really useful. You don't get that benefit for cheap and easy cooling that you used to have. So the best way to achieve balance is to actually reduce whichever load is too big. And where we are, that tends to be our heating loads. Here's a great benefit for us. If we have a heat pump with a coefficient of performance of 4, that means you put in 1 unit of heat of compression energy and you get out 3 additional units of heat that you moved from outside or from the ground into your inside. In cooling season, you have to reject that heat of compression. And that means that if your annual cooling load is 75% of your annual heating load, the ground will actually be in balance, assuming this heat pump is about coefficient of performance of 4. And the more efficient your heat pump, the closer they have to be in balance, because the less electrical energy you're using that's in heating. So for us, for the most part, that means better insulation, better air tightness, lower U factor windows, ventilation heat recovery, and actually designing for passive solar gain. In other words, if we can reduce our annual heating load, this is not the peak heating demand, which is a different story. This is just annually. If we can reduce the total amount of heat we need to extract from the ground so that it's roughly only 25% more than whatever our cooling load is, then we're in balance. And then we can have a small, reasonably sized geo-exchange system. If it happens that our cooling load is too large, then we can also use night flush cooling, economizer cooling, all these passive approaches to try and reduce the cooling load, to try to make them balance. So ideally, you end up with loads that put the geo-exchange system in balance. We can also mix geo-exchange types. So this is an image of a slinky loop. And what you can see is at different depths, we get different temperatures at different times of the year. And so we can, we have computers and they can sense the water temperatures, and we can open up different valves to have different sources of heat exchange happen at different times of the year. So in this case, we might want to start our heating season using the slinky loops, which have spent all summer gaining heat from the sun, right? And then sometime around late January, early February, we might switch over to a few borehole loops that are deeper in the ground and are at that constant 50 degrees temperature, so that we can later in the cooling season make sure that we reject all of our heat to that borehole field, while the slinky loops are gaining heat all summer from the sun. And then we switch over to the slinky loops again. And that way we can have a smaller total system and spend less on each component while having sufficiency for both, especially if we've got an imbalance and we have more heating than we do cooling. So this would be one other way to make things work. Okay, so water source heat pumps. We basically have a few different kinds of options. One is, and this is probably the most common right now, is ambient water loop. So basically a building, in this case, has a piping loop that circulates through the entire building, and it sends around ground temperature water. It doesn't raise nor lower the temperature of the water. And then individually in each room or each zone, there is a heat pump that sends that water through a heat exchanger, uses the compressor to raise the temperature or lower the temperature as needed, and then blows air over the refrigerant, just like an air conditioner, or just like a air source heat pump that you might be familiar with if you've got like a mini split or something like that. So the benefit of this is modularity, right? You just buy all these individual heat pumps and put them around your building. You only have the one piping loop. You can do simultaneous heating and cooling because they're just either rejecting or accepting heat from that circulating water loop. And you're doing heat recovery. That water loop may be circulating inside the building, not interacting with the ground at all, and simply taking heat from, say, the server room and sticking it in the office, that, you know, the corner office or whatever. And so it's just moving heat around that way. The problems are fan power, right? It's an air-based system. It blows air that's not as hot as that blast of warm air that we're used to from a furnace. And so for some people, if it's blowing too hard, you actually get a discomfort thing because the air is blowing just a little, not quite warm enough. You also have the compressors inside the building. And so that creates a noise issue. And either if we want an inverter-driven heat pump, which is the way we have our current air source heat pumps, the reason they're so efficient is because they're inverter-driven. They're constantly adjusting their speed as opposed to turning on and off. But those ones are pretty expensive. And so more commonly, people get a simple on-off or two-stage heat pump. And then you get this penalty. When it turns on, it takes a lot of energy to get it up to speed, and then it turns off, and it's waiting, and that on-off cycle gives you a big penalty. Another approach is to take that water, that geo-exchange water, and run it through a central heat pump that makes hot water, or in cooling mode makes cold water. If you set them up, because you're going to have multiples of these, you can set them up to do heat recovery from one heat pump directly over to the other. They're quiet because they're out in the mechanical room, and all you're doing is circulating water, which is then going to, say, a radiant system. Radiant systems tend to be considerably more comfortable than air blown systems, so you get a comfort benefit. There's lower maintenance cost because instead of running around a giant building and fixing all the little heat pumps with all the things that could go wrong with them and all the filters and all that stuff, you have just one unit or one mechanical room that has regular maintenance. In this case, we don't need, especially at these kind of larger scales, we don't need an inverter-driven heat pump if we have a buffer tank, basically just a tank on the distribution system. It can allow the heat pump to run long and not have a penalty from short cycling. And because we're moving water around instead of air, we use a lot less energy for pumping. The problem is, if we design for high water temperatures, we're going to have a problem. It's not going to work very well, or it's going to be inefficient. If we want to do heat recovery on the heating and cooling, then we need a 4-pipe system, and that means twice the piping cost as we would otherwise. And unlike the water to air system, where the heat pumps are distributed around the building, in this case, we actually need a mechanical room. We need some sort of central space. So depending on what you're trying to do.
And can I ask you
yes,
to wrap up?
I will. So there are reasons why not VRF, and we can go into them, but one point is air source heat pumps are really quite efficient and they're getting more so. So you have to have a pretty good reason to want to do a geo exchange heat pump. We can talk about some of these other things, which I'll just skip, but I will point out that there are air to water heat pumps where all those benefits of the water to water heat pump can also be acquired from an air source heat pump if you don't want to make a big hole in the ground. And by adjusting water temperatures, we can actually get really, really high efficiencies comparable to a ground source heat pump using an air source heat pump. Thank you.
So Ben, this is very complicated in my humble opinion. And one of the things that I was confused about is how deep you have to drill in the geothermal systems. Is it that the closed loop versus the open loop systems have different depths? Could you clarify that?
Okay, very good. So the depths for drilling, if you're doing a vertical closed loop system, you will tend to be going between 200 and 500 feet down. For a horizontal system like the slinky loops that I described, you might only be going 4 feet, 6 feet, maybe 10 feet down, depending. You could even layer them. But you're going a long distance out. So it really depends what you're going to excavate. If you've got an open loop system, like a well, that could be as deep as more than 1,000 feet down. Yeah, so that could be quite deep, or in the 500-foot range. Really depends on the geology. I think that the real story is it all depends on the geology.
Wow.
Yeah.
Okay, so if what you're trying to do is pair your geothermal system with air source heat pumps, and you want to run them off of solar PV panels with battery backup, so that if the grid goes down in the middle of winter, you're still going to be able to heat the building. What it seems to me, as a layperson, that's an advantage for using the geothermal system right there, because you need less electricity to run your heat pumps if what you're dealing with is ground temperature air rather than air temperature air.
Yeah.
Ground temperatures rather than air temperatures.
So generally, so what we're actually talking about now is the coefficient of performance, right? What amount of electricity do I have to put in to provide heating? And that really depends on how cold it is outside, whether this is a benefit or not. So you saw that the most common temperature we experience here is roughly around freezing, right? That's the kind of our median heating season temperature. And that means that if the power was out for some relatively short period of time, we should probably bet that we're going to be around freezing. And at that temperature, air source heat pumps these days, well designed, that's a big if, well designed, well specified, can have a coefficient of performance of around 3.5 to even 4. And a ground source heat pump at that, at the 50 degrees, whatever, can have a coefficient of performance of around 3, assuming again that system coefficient of performance was low. In other words, we didn't spend a lot of money pumping the water around or blowing air around. So if we're not doing those two things, then the ground source heat pump might be a low enough power requirement that you could satisfy it with batteries. But you could also do that potentially with an air source heat pump, again, if you had the system efficiency right. So it's a yes and no, maybe, depends on how big your batteries are and how big your system is.
So it sounds very complicated to me, and it sounds to me like if there's a specific question, like for example in Amherst, where they're considering building a school and trying to make decisions about that you would have to have a very knowledgeable consultant factor in all of these various factors and come up with some recommendations for how to proceed. It just doesn't sound to me like a simple answer.
This is not a seat of your pants sort of the solution. If Amherst, and I don't know deeply what Amherst is planning to do, but if there's a plan to use some form of geoexchange, finding a really good geotechnical and soils engineer to investigate, and generally you're going to drill a test well, and find out what is the conductivity of the soil, what is the moisture of the soil, if you're going down to bedrock, how close is the bedrock, all of those questions you're going to want to investigate and really understand the thermal characteristics of the potential geoexchange system. But remember, that second half of everything I was talking about was how the distribution system is key to actually defining whether this is going to be efficient or not, regardless of that ground, of whether you're using ground or air source. If you can have, and that's something that is, I mean, also requires a good engineer to design well, can be designed well regardless of what the source is going to be.
And to your knowledge, are there engineering firms available locally that are accustomed to doing this sort of consulting?
Yes, more close to Boston and quite a few in places like Albany, Syracuse. And to be honest, a bunch of Canadian firms. You know, if I were looking for somebody who was really experienced with geothermal and heat pumps, I might be looking at some Canadian firms. Sally, you had a question.
Yeah, I was just wondering, related to that, I know that UMass Clean Energy Extension, Ben, where you are, does help municipalities explore projects. I just was wondering if that's something that would be within the scope of UMass Clean Energy Extension to look at and make recommendations for municipal buildings.
It is. I mean, so that's what I do. And I generally am working with, so I'll work with municipalities to try and meet their needs where they actually are. So if they're in the early design stages, I may act more as a owner's advocate to work with their design team to make sure that their design intent is covered. In many cases, it's a retrofit situation where we try to understand what's the best option available for an existing building. You know, so in a case like this, where let's say it was a brand new building and the intention was to go with a geothermal system of some sort, ground source heat pump system, I might try to help them find a good consultant to do the geothermal component. I would probably help them or help their MEP company design a compatible and and appropriate distribution system. But these things tend to take more than one player to put all the pieces together.
I just want to let you know, Ben, we have a bunch of questions that we've collected before the meeting and that I've been collecting since. So we're handling the questions. That's all right.
Sorry, I
Adele, so Ariel, if you could chat to me your question, then I'll pass.
Oh, I see what we're doing. Right.
So, Adele, did you get through the questions that we had?
Some of them are, so this presentation was more complex than I was expecting. And so some of these questions are in my opinion, not really relevant anymore. So Andrew, why don't you go into whatever questions you've been gathering, and if you can find some that you think are answerable in the amount of time we have.
Okay. One question is, what are the range of costs for a homeowner looking to do it?
So let's see. Generally speaking, you could say that it is that just the ground loop portion of it is in the range of $5,000 per ton, right? So a ton is 12,000 BTUs of design energy demand, right? So we'd have to understand what's the design energy demand for a typical house. Let's say a typical type of house with the type of homeowner who's likely to have the type of money required to do a geothermal system. They might have a five ton system that they're designed for. So $5,000 per ton. And then you've got to get a distribution system. And let's say that is about, I don't know, $2,000 per ton, just ballparking it. It adds up. So we're talking about something like $40,000 to $50,000 in that range, more. There's a reason why you don't see a whole lot of geothermal systems in typical residential applications.
One question that had come in earlier was about refrigerants, and that sounds like a pretty straightforward question. It seems like the systems that you've identified don't actually use refrigerants except until you get to the air source heat pump side.
No, that's not true. All of them use refrigerants.
Okay, great. Thank you.
And the difference is in a typical water source heat pump, the refrigerant is essentially inside the machine. It's a factory, it's factory sealed. And so you use less refrigerant because you don't have refrigerant lines snaking all over your building. You have refrigerant just inside the machine itself between, the condenser and the compressor, the evaporator. And because it's factory sealed, you don't have as many opportunities for leakage as you might have with lots of field connections. So that's a benefit. Now that could be the case with an air to water heat pump as well, where it's also contained inside the module and you're just making a water connection. So generally speaking, these shouldn't leak, but we certainly have leakages, but there's much smaller volume of refrigerant than, say, a variable refrigerant system, which is sending little copper pipes all over a building and connecting them in lots and lots of places. And each one of those connections is made in the field by a human being, and human beings are fallible.
Okay. Andrew, do you have some more questions?
Yeah. Do you know about the proposed geogrid system that?
Yes. So this is the best thing since sliced bread. So what makes this a great idea is, remember, I said, well, for every ton, we're going to have to spend $5,000, and who has that? Well, it turns out that if we're all connected to the same geo exchange system, maybe it's running down our street where the gas line used to be, then I might be demanding heat right now, but you might be demanding heat a little bit later. And even better, let's say you're a house and I'm a grocery store, and I have a lot of heat rejection to do. I'm basically a giant refrigerator, so I need to reject heat, and I'm going to send it into the geo exchange loop, and you're going to get that heat. It's barely a geo exchange loop. It's really just a heat exchange network between us. And now we're able to really maintain really good condenser water temperatures, really good temperatures for us to do things. And the more diverse we get, the better that is. And we share the costs, or in the case of the HEAT's plan, really the utility bears the cost, and they charge us for the heat, but because they're a utility, they can amortize it over 30, 40, 50 years. And so the overall cost is low.
And can that kind of system, how dense, do the buildings have to be for that kind of system to work?
There's actually kind of a sweet spot thing about it. So if you have mostly residential houses, right, where they're all kind of heating it around the same time and they're all cooling it around the same time, you actually need a fairly well spread apart system, because you're actually going to need, remember that thermal imbalance issue? You're going to actually need more boreholes. But if we have really high density of residential buildings, Well, they're still heating and cooling roughly at the same time. And now we either have to drill really, really deep to get enough heat exchange area, or we have to have some sort of advective heat flow, like a big, open loop system. It can work. But generally, if it was density of only one use type, then we actually could get too dense and we don't have a way to supply enough heat. We don't have enough capacity. But where we have density and diversity, we can get everything. So New York City is the perfect place. I'd say Holyoke in some cases would be a perfect place for a heat network like this at high density. And some of you may know that, certainly Adele knows that I've talked about this kind of a network in downtown Northampton.
And a couple of people have asked if you know what kind of incentives there are.
Pretty good ones right now. Mass Save is offering really good incentives for ground source heat pumps. And you can gain alternative energy credits. If you have 100% heat pump heated building, you can actually sell credits for renewable heat, essentially based on the coefficient of performance of your heating system. So yeah, that buys it down considerably and I would say, makes it much more affordable, again, given the right circumstances.
And is that state level incentive?
That's all state. Yeah, that's all in the Commonwealth. I see Sally raising her hand. She tends to know about incentives pretty well.
Is that okay if I jump in?
Yeah, go ahead, Sally.
Okay, so I just looked it up just to be sure. Mass Save is currently offering $15,000 for a whole house geothermal system. Plus, I believe there's a 26% renewable energy federal tax credit that's still, I think, through next year. And then the alternative energy credits.
Cool. So we're curious about the UMass plan and how that's going to work.
So I was involved with developing that. I'm on the Chancellor's Carbon Mitigation Task Force. The basic plan is kind of twofold. Lower the water temperature required. So right now, UMass uses steam to distribute heat, and then that steam is converted into high temperature water in most buildings. In some buildings, they use the steam directly. So over the next decade, basically, UMass would be burying hot water and cold water lines. It already has some chilled water loops, right? They've got a lot of large chillers. And then there would be, essentially, you have the chillers, but there'd be different ones that are right now designed to make cold water to circulate for all the time. And instead of rejecting that heat to the air like it does now, it would reject heat into the heating loop. And so we'd get both heating and cooling at the same time. UMass has a lot of cooling demand, even in the winter, because we have rooms that we fill full of students that are inside of buildings so that they don't have any way to lose heat to the outside, because there's like a hallway or something all the way around those giant rooms full of students. Then we have laboratories, some of which generate a lot of heat, and we have computers. So we have a lot of reasons for having cooling demand all year round. And this basically would be a way of taking that heat and moving it efficiently to where it's needed. That accounts for a fair portion, but it's not quite balanced. And of course, it's not always exactly at the same time that you need heating and cooling. So then it would reject heat into the ground, a big borehole field, just like I described, of just U-tubes going down about 500 feet out in the athletic fields. And that would do, I think that's something like 90% of the total heating load. I'm still in trying to push for reducing heating demand, because then if we got things truly into balance, then we wouldn't have to use any fossil fuels at all. Right now, there's kind of a not exactly a plan for how to make up for that imbalance. But really the answer is just insulate, air seal, better windows.
So this is a question from Sally. What about retrofitting systems that currently use baseboard hydronic systems, but with fossil fuels? Can those be switched out?
Yes.
Is that happening?
And, but it's not free. Unfortunately, a lot of these things cost money, and right now there's not a lot of support for these costs. So the key thing, as I started to point out at the very end of that presentation, the key thing is lower water temperature. The most comfortable form of heating and also the most efficient is underfloor heating, right? If you can circulate water that's like 80 degrees, and then your heat pump, even an air to water heat pump, is operating at a coefficient of performance of 4 or 5. So that, remember, if it was about that delta T, how big was the temperature lift that we have to do? Well, one way is to raise the bottom by going underground, and the other way is to lower the top by expanding the surface area of your heating system. So for those who want a comfort upgrade and a quietness upgrade and maybe an aesthetic upgrade because they can get rid of those baseboards or whatever, and you've got the accessibility from below, underfloor heating solves your problem. You know, you just staple up PEX tube with a little heat exchange plate, and then you can use a ground source heat pump or an air to water heat pump. A lot of us can't do that. If you wanted to argue to yourself, well, I'm going to really want some cooling, then you could essentially clip out those baseboards, those fin tubes, and install fan coil units that are designed for low temperature hot water, and they can also do cooling. And now you're getting something else that you actually want. So it's actually, that's kind of what I'm trying to arrange, both of these in combination for my mom. But
very interesting. And another question was, does having a high water table help?
yes. Yeah.
A lot of
Because
this area has.
Yep. That's why it's a perfectly viable system for here. Because then in a lot of places we already have well water, like people who are already on wells. So we already have lots of well drillers around here who are perfectly good at it. And if you have a high water table, then the lift, right, the amount of work that your pump has to do to move water, the lift is not from the bottom of the well. The lift is from wherever atmospheric pressure is affecting the water and how much higher you have to lift it to get it into your building. And so if the lift is really low, then the pump doesn't have to work that hard.
Rudy, do you want to ask your question? I think I missed it. You there, Rudy?
Yeah, it looks like he's unmuted.
Oh, the question I sent in, I think I'm going to pass on that. It's sort of off the topic of the geothermal per se.
All right.
Thanks.
So shall we move on to the rest of our meeting, or shall we take another question?
If anybody has a general question that you would just clarify everything for you, welcome you to ask that right now, and then we'll move on. I know I'm going to have to listen to the whole thing all over again.
Yeah, I think I might have to listen to it, 5 or 6 times before I'll understand it myself.
That's not great. Sorry.
Yeah, we're activists, not, technical experts.
Yeah, no,
Wait,
but
some
I
of
was
us are
trying to reach
physicists.
that. I'm sorry, Lori.
Some of us are physicists.
Oh, yeah.
Okay.
Well, you understand it then.
Laurie will explain it to us at the next meeting. So do you think that geothermal in general makes sense for towns to pursue?
To share. The bigger the shared system, the smaller the heat exchanger with the ground you need, and the more the ground just acts as storage, as opposed to you've got to try to pull it in some other way. And the more you have, again, the more diversity of the loads, the more you're just using water as a heat exchange fluid between systems. And yeah, so I think it's really got to be where we go in a lot of cases, but doing it by ourselves, the solitary homeowner, it's not cost. It's hard to justify on cost, and it's not that much better than air source heat pumps for just typical residential applications.
So it sounds like what you're saying is our school in Amherst would benefit from extending the system to include homes as well, so that there's different users at different times.
It could. Now, there are complexities about creating a utility, right? Being able to sell heat, having people agree to contracts where they trust your heat meter and that it's utility grade. And I mean, it's easy to say how to do, and kind of getting it at the level of precision that people like is another thing. But if a bunch of people, say a homeowners association, bought into it and basically created their own component, that could work. The bigger it is, the more diverse the loads, the better. But the other thing is, with a brand new school, if you're actually building a brand new school, you can insulate the heck out of that thing such that you actually do bring the heating and cooling loads into balance. It's very hard to do with existing buildings. With a new building, you could choose to have a distribution system that uses extremely low temperature water, like say large radiant panels, whether it's floors or ceilings or whatever. And then you have just less fluid to move around overall, less air to move around. Again, new building, you can do whatever the heck you want.
Lisa asked one more question to me. Are some towns in, socialist countries, democratic socialist countries doing this
Yes,
already?
most of Europe, especially Northern Europe. They've been using water source and particularly ground source heat pumps in Scandinavia all of my lifetime as the, like the primary, that's what people did. Basically, after the 1970s oil crisis, that's when they got going on heat pumps. And there are towns, I'm blanking on the name of it. There's a town in Finland that basically uses water, not ground temperature, but basically uses water and I think it's an ammonia refrigerant is the refrigerant, and they heat their entire city with low temperature, medium temperature hot water. They have enough of it that they also do snow melt, so they don't have snow plows.
Wow, that's systems thinking for you. Well, thank you so much, Ben. This has been.
That would be a great way to solve our pothole problem too.
Yep.
Great.
Here,
We do
here.
have some updates on local projects that we're working on. None of them yet are installing geothermal ground source, but we aspire to have help make that happen. Because what we're all about is instigating, doing the research, putting the ideas out there and advocating for innovation locally in our energy systems. So it gave us a lot of food for thought.
Yeah.
People would like your slides. Will you send those to us so we can send them out?
Yeah, that's because Adele's the person I email with a bunch. I'll just send them to
Yes.
Adele.
That'd be fine. Yeah,
Great.
thank you. Thanks so much, Ben.
Yeah,
Thank
thanks
you
for having me.
so
Sorry it
much.
went too wonky, I guess.
I'm sure
Thanks, Ben.
Lori
Fascinating.
appreciated it.
Yes, indeed. Thank you so
Um,
much.
So yeah, so let's move right into update on our projects. What's happening with Habitat, Adele?
So Habitat for Humanity had its wall raising last week. And we were, some of us were there. Maureen Carney and I were there. It was virtual, by the way. Local energy advocates had its name up in lights. They showed a slide of all the various groups that were helping to fund the project. And we were listed. So I just want you all to know that, you know, we are officially contributing to the Habitat project. And there are walls that have gone up. So, but the houses won't be complete until, you know, probably about a year. And the hot water systems that we're helping to finance probably won't be purchased for almost that amount of time. So, but nonetheless, they're still moving forward with our ideas based on our research for better hot water system than they were planning to include in the first place, which was resistance hot water, because they don't have basements in the houses. So therefore they couldn't use regular hot water heat pumps, air source heat pumps, which are usually in the basement. So we were recommending the solar assist heat pump, which has an outdoor unit, which is the heat pump, and then the indoor unit, which is the hot water tank. And that's what they are going to do. And we're going to pay the incremental cost. So that's moving along, and that's great. And Maureen and I, unfortunately, Maureen was injured at the library. That's I guess libraries are dangerous places these days. Some guy ran into her at the library, knocked her over, and she now has a fracture and is going to have surgery. So, but in any case, Maureen and I did also meet with Karen Baker of Valley CDC over at the new nursing home that they've purchased on Bridge Road, and they're going to convert it into eventually, which is going to $25 million project. They're going to retrofit this crappy old building into an energy efficient 60 affordable apartments. And we proposed that we would she was asking whether we would be interested in, as an organization, in raising funding for photovoltaic panels. And we said we would be more interested in perhaps considering helping them raise money for geothermal systems. So they're in the process of looking into that. It's obviously a multi-year project and with a very high price tag, and they're going to get money from many, many sources. But it's very exciting. So that's my update.
And I actually don't see anyone who I don't think went off from the last meeting with some research to come back and report on. Is that true? Is there anyone who has something to report in on? Laurie?
Yeah, I was going to, I think this is the place I said I'd get back to you about my experience with block power. Yeah. So I'm working through it. They are actually in the process. It takes time. I sent them a whole bunch of information, and they're going to get back to me with a plan for converting my house. So I thought that was sort of cool. I haven't heard the plan yet, but you know, I had to send them a whole pile of gas bills and electric bills and information from Mass Saves, and I forget what else. So when they come back with it, we'll see what they, you know, I couldn't get all the information I wanted all at once. I may have to come back next month and tell you what, if anything, happened, because I don't really understand exactly how they work yet either. I think I'll understand it as I work through the process.
Yeah, yeah.
Are they charging you, Lori?
No. No, they're going to do this plan, and you know, they come up with some sort of plan, and they get paid if you, I think if you buy their lease, right? So the deal is they lease you the equipment for 15 years. And the price is not supposed to be any more than what you would pay for heat. And I think in my case, they've already told me that in most places that's $300 or $400 a month for, and it's not that high if you're using natural gas in this part of the world, which is what I'm doing right now. If you're using propane, it is, but not if you're using natural gas. So they may have a hard time finding a plan that works for me. They guarantee you that it will be lower than the lease price will be lower than what you're currently paying.
Sally.
Just a clarification question. What kind of system are you having put in?
It'll be an air source heat pump system, and I think they are going to want to do splits everywhere. I've been trying to figure out, one of the issues that I have is I have some very expensive instruments in my house, musical instruments that cannot be subjected to the dry air around here in the winter. So if I get rid of my furnace with its steam humidifying system and my ducted hot air, right, how are they going to do that? So we haven't talked about that yet either. It's all step, you know, piece by piece. I'll get to all this information and see if they can deal with it. So I do have some proposals now for how to do that. I also talked with Mass Saves, some of my specific. So you can also call Mass Saves. That's something I found out that I didn't know, is if you have specific questions about your house and how to convert it, you can talk with somebody at Mass Saves, and they will, you know, you can describe what your house is and how it's currently heated, and they can tell you over the phone what they think you'll need to do, you know, what your requirements are, like me with the humidity. So I had a very good conversation with a guy at Mass Saves who answered a question I've had forever on how I now know how to solve that problem. And I'm curious to see how Block Power comes up with a solution. Because I don't think.
Did you talk to somebody at Center for Ecological Technology?
No, I just called, I can give you the phone number. I just called the Mass Saves number, a general number.
Yeah, because I would be careful with the information that you get. It can vary.
I'm sure it can, but I also, I mean, I had a pretty technical talk with this guy, and he answered. So I'm coming at this as a physicist, and the local technicians couldn't answer my questions, and he could.
Okay.
So I finally understand why the ducted system is so much less efficient, and actually that was explained today too. None of these places like to do ducted systems with air, with forced air, because they're very inefficient because of all of the extra power needed to push the air around.
And the heat loss through the ducts if they're not well
Yeah,
air
that
sealed and insulated.
doesn't make sense to me though, because the heat loss is directly into the house. Anyway, that was the part that never made
Okay,
sense.
but here's a service you could provide all of us, is to
Mhm.
have Sally come over, because this is the kind of advising she does, and get 3 different routes for, you know, advice on how to convert your house, and using Block Power, Mass Save, and Sally.
I would love to know.
Andrea, I'll give you commission.
Yeah, you have
Thanks
to
for the
pay Sally.
commercial.
It's not free.
I may not be technical enough for Lori.
All right.
So I'm just interested, Lori, you would be leasing the mini split heat pump system?
Yeah, the way Block Power works is they come in and they do everything for you, and they write you a lease where they you know, you're leasing the equipment from them, and at the end of 15 years you can either buy it from them for $1 or you can write another lease and they'll update everything, right, if it needs updating. So that's how they work. That's how they make their money, is through these leases. You know, they just come in and do it. And you know,
So you don't need the Mass Save incentives,
Well,
because you're
they'll use them.
leasing.
No, they will use them and that will get folded into the price on the lease.
Oh,
But do they do, I mean, will they look at your house and say, well, you also need triple glazed windows, you also need, you know.
That's what,
all the other
yeah,
things.
that's what they wanted Mass Saves to do. That's Mass Saves comes in and does that. They work with what you have, and they supposedly will send somebody out here to look at the house at some point. And I'll be interested when that finally happens. They're trying to find they don't have a local partner here yet. I thought they did. So they're trying to find a local partner to send out here. So I think they're using me as a wedge into the community.
I've never heard of them. Just to be sure, a bit of free advice. If you're getting a whole house air source heat pump or mini splits, make sure they do a heat load calculation to see what they cost.
Yeah.
Okay.
Manual.
So I had a conversation with Ashley Musprat, who is now now been named the director of CET, the Center for Ecotechnology. And she's very interested in partnering with Block Power. So it may very well be that, you know, that will emerge and that they will be a local partner. Let's hope, anyway.
What was the name of that? That's
Center for CET, Center for Ecotechnology. It's located here in Florence. It's a very good organization as far as I'm concerned.
but they only work with Berkshire Gas customers. So,
Well, right now, but if they were to create a partnership with Block Power, they might expand to, you know, many other venues.
In the past, individual homeowners and other people building have been able to hire CET experts for, you know, helping design things. I don't know if that's still the case. And it's not through Mass Save, it's a separate thing. So I don't know what their, you know, geographic area is.
Yeah.
It's been expanding for sure, the geographic area.
So Mark Newey there is very smart. He used to work at NASA, of all things. So Lori, he might be a good fit for you.
Oh, yeah.
Yes.
All right, we are running out of time. I think that was all for now on our follow-up to Block Power. Thank you, Laurie, for following through and reporting in. We'll get it in installments.
I'm seeing some interesting comments in the chat, and I'm wondering if somebody will save the chat so we can
Yes, sure.
process them
Susan's
later.
made some.
Um,
Oh, you're always welcome, Susan. We consider Berkshire's Western Mass. So we're not just Pioneer Valley. Yeah, so I think that's all for projects. Just we are still building our team here, and our if Sally's cat would like to join the board, we'd really welcome her. We're looking for people who'd like to be more involved and help us create new programs and new projects. So to be continued at our next meeting, which did we decide we're going to do in a month? People want to come back in a month for another topic and reports. Hopefully some of the others from last month will be able to come in.
Yeah, let's do there were a bunch of people who were going to be doing research, and they were not able to make it to this meeting. So I'm eager to hear what they found.
Yeah. So we try to do the third Tuesday night of the month. So look for our announcements. Thanks so much for coming, everybody.
Thank you.
Yeah.
Thank you. It was
Thank you.
interesting.